Hello students, and welcome to our lesson on mathematical modeling. The whole point of this lesson is to get us to practice writing down equations that are described using words. So only word problems or applications in this lesson. But really what we're trying to do is make sure we understand that linear and quadratic situations are all around us all the time. And so some of these are going to be very mathematical sounding, and others are going to be totally reasonable things you might encounter in real life. And just know that the options are limitless. We can only pick so many examples for a lesson, but all around you there is mathematics that you can be figuring out. And so even though this is only going to touch on a few situations, just know that as you're going through your life, you should be constantly thinking, hey, can I figure out the answer to this? Because you don't have to guess all the time. In a lot of cases in real life, we do have enough information to actually solve the problem and give a real answer. So that's what we're going to be practicing here is how to get to real solutions to problems. So a couple general strategies that we're going to be following, at least for the most part. First thing we want to do when we are trying to model things mathematically and get to solutions is, of course, we want to read the problem. If you don't know what the problem is asking you, the odds of you solving it are pretty low. And then we are going to mark up the text. So we're going to do a little highlighting, underlining, whatever we got to do. I tend to do less and less of this as I get more comfortable with the types of problems I'm doing. And you will probably find yourself being the same. But at least at the beginning, I recommend you practice marking up the text as a way of training your brain for what to look for as you're reading the problem. Okay, then we're going to get organized. This step sometimes is unnecessary, but we're going to see, especially on the last two examples we do in this lesson, having a table is going to make our life so much easier for understanding what the equation we need to write down is. And so that organization sometimes is as simple as just drawing a picture, like we're going to draw a couple rectangles in these. And sometimes it's more complicated, like making a list, making a spreadsheet, something like that. For today, though, really just drawing pictures and making tables is all we're going to need. All right, and then we're going to do the hard part. We're going to write an equation that represents the scenario. This is what that organization is going to help us get to, is that equation. And then finally, the easy part, I would argue, because we already have the skills, is we are going to solve that equation. But of course, because these are real life applications, we have to make sure whatever solution we get actually is possible. So there's going to be a couple problems in here where we get multiple answers and we have to throw one away because it just doesn't make real life sense. So always at the end of these, you got to check, hey, does this solution actually fit real life or do we need to discard this answer? All right, first page here, we're going to be doing some linear examples. So number one, we're going to dive right into it. We have 5 times the sum of 3 and twice a number is 70. Find the number. The first thing I always like to do when I'm reading the text or the problem is figure out what am I looking for. So in this case, we're trying to find the number, and since we don't know what that number is, we're just going to call it x. Okay, you can use whatever letter you want, but generally in mathematics, we stick to x unless we have a reason not to. So we're going to try to find that number x. So now we need to organize the rest of this information so we can write an equation to find that x. So it says 5 times the sum of 3 and twice a number is 70. Okay, every word in that sentence has a very specific mathematical reading. So the number 5 is the easiest part. It's just a 5, right? 5 is just a number. But then it says times, so that's going to tell us to multiply. Whenever we're doing multiplication, most of the time we're going to use parentheses. But for this step, I'm just going to write the multiplication dot to get us used to it. Then we have the sum of 3 and twice a number. So the word sum is going to mean to add. But what are we adding together? Well, we're adding together 3 and twice a number. So 3 is just 3, but what am I doing with 3? I'm adding it to twice a number. And hey, we know what that number is, not actually, but we know what we're representing it with. We're representing with x. So if x is the number, what's twice the number? Well, all you do is throw a 2 in front of it, okay, twice right there, and it's 2x. So again, every word there meant something. The word sum told me to put this addition symbol in between. And then 3 was the first part of the addition. And twice a number, which is 2x, is the second part of the addition. So what we're going to be doing so far is multiplying 5 times this entire sum, 3 plus 2x. All right, and then the last part of this says is 70. The word is will always mean equals for us in math, and then 70 is just a number. So if we throw all this together, we have 5 multiplied by 3 plus 2x equals 70. 5 times the sum of 3 and 2x is 70. All right, so the hard part is done. We have written the equation. Now we just go ahead and solve. So we can solve this in whatever method we prefer. I'm going to go ahead and distribute the 5 first instead of dividing both sides by 5, but you can go about that either way you like. So after distributing the 5 into the 3 and the 2x, I get 15 plus 10x, still equal to 70. And then I'm going to go ahead and subtract the 15 from both sides to get 10x equals 55. And if we divide both sides by 10, we get that x is equal to, we can either write it as a decimal or a fraction here. So we could write 55 over 10, which is unreduced, but we can also reduce that. If we divide top and bottom by 5, we can get 11 over 2 as our answer. Or if we want a decimal, we can call this 5.5. Okay, all of those are perfectly fine as answers. So then whenever you get to the end of an application, you always want to make sure you clarify what your answer actually represented. So in this case, we got 5.5 as an answer. So we would say that the number is 5.5. Okay, so at the end of applications, you should always be writing some sort of sentence that clarifies what your solution was. All right, number 2, very similar problem where we have this very rigid mathematical structure. 2 more than a number is 12 less than 3 times the number. Find the number. So again, we're trying to find a number. So we'll call that number x. And we can see that the word number showed up a couple times in here. Okay, we have 2 different spots where we see number. So all we have to do now is diagnose what the words around it mean. So the first sentence before the word is, okay, and I say before is because right here, this word is, that's going to mean equals for us. So before we get to that word is, it says 2 more than a number. Well, what does 2 more mean? It just means to add 2 to the number. So 2 more right here is going to tell us to do plus 2. And we're going to be doing that plus 2 to the number x. So the left side of our equation will just be x plus 2. Then we have that equal sign. Now we're going to look at the other side of the equation. So it says, is 12 less than 3 times the number? So if 2 more meant to add to, 12 less means to subtract 12. And what are we going to subtract 12 from? It says 3 times the number. So we already know the number is x, and 3 times x means 3 multiplied by that x. So the right side of our equation, 3 times the number is 3x, and 12 less than that is 3x minus 12. All right, now we can go ahead and solve for x. So this time I'm going to move all of the x's to one side, all of the constants to another. So if I subtract x from both sides, I'm going to end up with 2x on the right. And if I add 12 to both sides, I'll get 14 on the left. Then just divide both sides by 2, and we get that x is 7. So now we need to summarize our answer again because we have a word problem here. So we're going to say that the number is 7. And for all of these, we can always go back and double check if it actually meets the description. 2 more than a number. Well, if the number is 7, then 2 more than a number is 9. Okay, and so 9 is supposed to be the same thing as 12 less than 3 times the number. Well, again, if the number is 7, 3 times the number is 21, and 12 less than 21 is 9, which is exactly what we said the other side of the equation was equal to. So you can always go back and make sure that your solution is plausible for all of these. All right, this one's going to be a little bit more involved in terms of real life application, which makes it a little bit more fun in my opinion. It says a patient receives 3 doses of a medication over 3 days. The total dosage administered over the 3 days is 96 milligrams. If each day's dose increases by 1 milligram, how much medication did the patient receive on the first day? So what we are actually looking for in this problem is how much did the patient receive on the first day? So since we don't know what that amount is, that will be our variable x. Okay, we're trying to figure out what that first day's dosage. So now we got to put together what we know. There were 3 doses given, and the total dosage over those 3 days was 96 milligrams. So because it says that there was 3 doses and that the total dosage was 96 milligrams, that means that when you add together the 3 doses, you get 96 milligrams. So if we add together the 3 doses, which we can call x, y, and z, okay, because we already know one is x, so the other 2 can be y and z, we would have that x plus y plus z equals 96. Okay, and then just to clarify here, this equation means the 3 doses total 96 milligrams. All right, so we have an equation that does something for us, but notice that there's too many variables in there. We don't know how to solve for x, y, or z in that equation because we don't have enough information yet. We want to try to get this down to where there's only one variable. So we need to use this middle line that says each day's dose increases by 1 milligram. Okay, each one goes up by 1. So that means we have a relationship between them. Okay, if the first day's dose was 10 milligrams, let's say, that would mean day 2 was 11 milligrams and day 3 was 12 milligrams because you just add 1 each time. But since we don't know what the first day's dose is, that's what we're trying to find, we have to use x as our base. So we know that the first day was just x. Okay, so first day's dose is just x. That's what we decided is our variable. That's what we're trying to find. But if that first day's dose is x and it goes up by 1 each day, that would mean day 2 is going to be x plus 1 milligrams. So that letter y, which represents the day 2 dose, is 1 bigger than the first dose. So x plus 1. Then we have day 3, where we're going to go up by 1 milligram again, but it's not going to be x plus 1 again because we already went up by 1 for day 2. So for day 3, it's actually x plus 2 is the number of milligrams we're giving. So each day's dose here, okay, each day increases by 1 milligram. Okay, we start off with x, whatever that is, then we have x plus 1, then x plus 2. And now we can go ahead and solve, because now we only have one variable that we need to solve for, so we can go ahead and figure out what that is. If we combine like terms in this expression, the parentheses don't actually do anything here. I just wrote them to clarify x plus 1 and x plus 2 were y and z. But because we have addition everywhere, we can just combine the x's to get 3x, combine the constants to get 3, 1 plus 2 is 3, and this is equal to 96 still. So then if we subtract over the 3, we get 3x is 93, and divide by 3 to get that x is equal to 31. So we know that x is 31 now. We just need to clarify what does that mean in terms of the actual problem. And so this answer tells us that the first dose was 31 milligrams. And that is the solution to our problem. But now if we want to check if this makes sense, we can go ahead and figure out what does that mean for day 2 and 3. Well, if it goes up by 1 each time, that would mean day 2 is 32 milligrams and day 3 is 33 milligrams. And if you add together 31, 32, and 33, you will in fact get the 96 milligrams that is supposed to total. All right, number 4. It says a rectangular hospital room is being prepped for a new patient. The length is 3 meters more than twice the width. If the perimeter is 54 meters, what are the room's dimensions? Okay, a lot to unpack there. I always like to start, as I've said before, with what am I looking for? And so the end of the problem here says, what are the room's dimensions? And it's been talking about length and width in the first couple lines. So I'm going to say that we're looking for W and L. Okay, we want to know what are the length and width. All right, well, what do we do now, right? Because we have a lot to work with here. So this is where I feel it's best to draw a picture, if possible. You'll notice for the first couple problems, there wasn't a whole lot of organization happening because there wasn't a lot to organize. But here we have the description of a rectangle. And so let's just go ahead and put a rectangle on our paper. That'll give us something to work with. And then since we know we're looking for W and L, I'm just going to label width and length on my rectangle. All right, so all we have so far is a rectangle, nothing crazy, but we've also chosen 2 letters to be our variables. So now let's go ahead and see the relationship between them. It says that the length is 3 meters more than twice the width. Okay, so that's telling us how to write down what the length is in terms of the width. So our width is going to be able to stay the same. We can just say that the width is W, no problem there at all. And since the length is 3 meters more than twice the width, we can go ahead and say that L, the length, is, remember is means equals, so length equals, length equals, 3 meters more means to add 3, and then twice the width would be 2 times the width. So since the width is W, twice the width is 2W, and 3 meters more than that is 2W plus 3. So we now have that the width is W and that the length is 2W plus 3. All right, now we can go ahead and use that middle sentence that we have. It says that the perimeter is 54 meters. All right, so now we can go ahead and write an equation for perimeter, okay, where we know that the perimeter means to add up all 4 sides. And so if we go ahead and add together all 4 sides based on our picture, we're going to have that W is our first side. Then we have another W for the top side of the rectangle. So down here and the top one that's not labeled, these 2 W's. And then we need to add together also this length and this length, which are both 2W plus 3. So we're going to add 2W plus 3 and another 2W plus 3. And all together, this perimeter is supposed to equal 54 meters. So we can set it equal to 54. So this line here, okay, this one right here is just an equation for perimeter where I'm adding together all 4 sides of this shape. So now we can go ahead and solve because we only have W's in our problem. If we add up all the W's, we have 1, 2, 3, 4, 5, 6 W's. And 3 plus 3 is also 6. So we have 6W plus 6 is equal to 54. If I subtract 6 from both sides, I get 48. And then divide by 6 to give us 8 as our solution there. But we don't just want to know that W is 8. We want to know the room's dimensions, which means we need length and width. So we're going to go ahead and do an extra step here where we say that the length is equal to 2 times that width we just got plus 3, where this is using the middle sentence, which gave us this equation over here. Length is 2W plus 3. So since W is 8, that means that the length is equal to 2 times 8 is 16 plus 3 is 19. So we have our 2 solutions now. Okay, right here, 8 and 19. And we can go ahead and then summarize our answer. The dimensions are 8 by 19. And in this case, we are using meters as our units. So this room is 8 meters by 19 meters. And I could have labeled them as length and width there. The width is 8, the length is 19. But it should already be implied by the work that we've done here. But it is in no way wrong if you want to go ahead and add that label of length and width. All right, so now those were the linear examples, where if you've never done any calculations involving shapes in your real life, keep in mind that as you're growing up and you're buying houses and you're doing construction, all these different things that you might get involved with, that math does show up again. So in my own home, I've done things as simple as just adding baseboards, which are just straight lines that go at the bottom of the wall. But you do have to do a little bit of math. You got to go around your house measuring because the pieces come in one size. Usually 16 feet is the length of a baseboard, but not all your walls in your house are going to be 16 feet. And so you have to, set up some equations, do a little calculation, and figure out how many of these pieces do I actually need to not end up with a bunch of waste, tiny pieces when I'm cutting things off. So all that to say, if you try, you can find examples for this in real life. And sometimes even if you don't try, the math just finds you and you need to be ready for it. So hopefully that was a little bit of prep for you getting ready. Now let's do the harder ones. Okay, now we have some quadratics, which it just means that the equations are going to be slightly harder to solve. And by harder, I just mean they're going to involve a little bit more intensive techniques, but we are great at quadratics, so that's no sweat. All right, number 5. The width of a rectangle is 4 feet less than its length. Find the dimensions if the area is 96 feet. So just like before, I want to acknowledge what am I looking for. It says find the dimensions. And so I'm going to find the dimensions of a rectangle just like before. I'll label them W and L again, because since we're dealing with a rectangle like the previous problem, why not keep it as length and width? Because it describes a rectangle, I'm going to once again draw a rectangle. That way I have a visual to work with. I'm going to label my sides just like before as W and L. And then now I'm going to use the actual problem to see what to do next. So it says that the width of the rectangle is 4 feet less than its length. So width is 4 feet less than length. So that means width equals length minus 4. So where I wrote my W, I'm going to write an L minus 4 there. Okay, remember every word has meaning in these sentences. Is means equals. 4 feet less means to subtract 4 from that length. So we have L and we have L minus 4 as our two dimensions here. Now it says at the end of this problem that the area is 96 feet squared. Okay, well, we know how to get area. That's just length times width. And we know now that our length and our width are L and L minus 4. So we can go ahead and multiply those together and set them equal to area. So we're going to have length times length minus 4 is equal to 96. If we go ahead and multiply this out, we have that L squared minus 4L is equal to 96. And you'll notice now that we have a quadratic that's not quite in standard form. And so what we're going to want to do is move that 96 over so we can then use our either factoring techniques or the quadratic formula to get to a solution. So if I subtract over the 96, we have that L squared minus 4L minus 96 is equal to 0. And now we have to try to determine if this is factorable or not. So now in future problems that we're going to do just in a couple seconds, we're going to have to use the quadratic formula. So when you're solving applications, you always have an option of well, not so much an option, but you have to make the decision is, do I need an exact answer? In which case you should be doing pretty much everything by hand, or really everything by hand, or is an estimation okay? Meaning, can I get a rounded decimal as an answer and that satisfy the solution? In this case, whenever it's involving simple quadratics where we have a equals 1, I always recommend that you try to factor first. And by a equals 1, I'm talking about right here in front of this L squared. There is no coefficient, which means that that coefficient is a 1. That means it's probably easily factorable. But if we try to factor and it's not working, we can always default to the quadratic formula to get our solutions that way, which again, we're going to do in the future problems down below. So we'll see that later. All right, let's try to factor this thing. If you recall, I always like to set up a t-chart when I'm trying to factor, where I do a times c in the top left, which in this case, a times c is 1 times negative 96, so negative 96. And I put the b term in the top right, which in this case is negative 4. And then I try to come up with two numbers that multiply to give me negative 96, but add to give me negative 4. Which means I got to think, what times what equals 96? And so, you start racking your brain. And my brain, the first thing I was able to come up with is 12 times 8. But one of those is going to have to be negative to make it a negative 96 when we multiply. So I'll try 12 times negative 8. Okay, well, if I add those together, 12 minus 8 equals 4. So that's not quite right because we need a negative 4 when we add them together. All right, so let's switch the negative to the other side. Negative 12 times positive 8. If I add those together, negative 12 plus 8 equals negative 4. Then hey, we found the two numbers we need, negative 12 and positive 8. That means that when I factor this right now, I can go ahead and factor it to L minus 12 and L plus 8. Okay, so we can go back to our quadratic and our factoring, and we're going to go ahead and write in here L minus 12 and L minus 8. Sorry, L plus 8 as our second factor. Where notice that I didn't have to do all the steps of splitting the middle because we had a coefficient of 1 on the a term, so I'm able to skip directly to this step. All right, now we go ahead and solve by using the zero product property. So if I bring these up to the top, we either have that L minus 12 equals 0 or that L plus 8 equals 0, which means L either equals 12 or L equals negative 8. And this is where we finally get to decide, do we have answers that make sense? So first one is L equals 12. If L is 12, what does that make the width? Well, we said over here that the width is length minus 4. So if L is 12, that would mean that the width equals 12 minus 4. So width equals 8. That is one solution right there. Length is 12, width is 8. That seems entirely possible, and 12 times 8 does equal 96, so the area is correct. All right, so that seems plausible, nothing wrong there. But the other one is L equals negative 8. Can you have a length that is negative? Because keep in mind that a length is a distance. So the answer is no. We have to throw that one away because that one is not even possible. We cannot have a negative distance or a negative length in this case. So we only have one solution, and we're going to go ahead and summarize it here real quick. We're going to say that the dimensions are, and it's 12 by 8, and in this case we're dealing with feet. So we're going to say 8 feet by 12 feet. And that will be our final answer here. All right, not too bad, but you notice a little bit more involved there than the linear ones because we had to do some work with quadratics, and that's going to be the case in the next few, and they're only going to get harder. So let's see, number 6. 3 times the square of a number is 5 less than 16 times the number. Find the number. So just like before, since we're looking for a number, I'm just going to call that number x. And this one's actually not so bad in terms of setup because all we have to do is follow the words of the sentence and give each word a meaning. So we have 3 times the square of a number. Well, the square of a number, if that number is x, the square of x is just x squared. So then if we have 3 times the square of a number, that's just 3x squared. We just multiply the x squared by 3. Then we have that word is in the middle, which means equals. And on the other side, we have 5 less than 16 times the number, where again, the number is x. So 16 times the number is just going to be 16x. And we have 5 less than that. So if we want to do 5 less than 16 times the number, we just subtract 5 at the end. So I can go ahead and move this 16x minus 5 next to our equal sign, and we have our equation just like that. So when it's written in this sort of mathematical language, I actually think these problems are the easiest ones to set up once you've gotten a hand of the vocabulary, where each word really just does have a nice simple meaning. The part of this that throws most students off is the 5 less than part. A lot of students want to write 5 minus 16x, but you have to remember that it's 5 less than something. So you have to have the something first, in this case 16x, and then you're taking away 5 from it. Okay, so 5 less than, that minus 5 is in the back. All right, now we can go ahead and set up this as a quadratic in standard form by getting everything to one side. So if we move everything over, we're going to have 3x squared minus 16x plus 5 is all equal to 0. And now it's up to us how we want to go about solving this. So we can either try and factor it, or we can try and figure out something using the quadratic formula that hopefully will be a nice looking answer. Since we're going to be using the quadratic formula in the next two though, I'm still going to try and factor this one first. And it is going to work out to be factorable. So using the AC method, we can go ahead and make a t-chart like before. A times c is 3 times 5, which is 15. And the b term is negative 16. So we need two numbers that multiply to give us positive 15, but add to give us negative 16. Whenever the b term is bigger than the a times c, almost always it's just going to be 15 and 1. So that number and 1. So in this case, it's negative 15 times negative 1. And notice if you add those together, negative 15 minus 1 does equal negative 16. So our two numbers we're going to use are negative 15 and negative 1, which means we are going to split the middle over here. Instead of negative 16x, we're going to have negative 15x minus 1x, and we still have the 3x squared in front and the positive 5 in the back. All right, now we've split the middle. Now we're going to do factor by grouping. So the way we do factor by grouping is we split the problem in half right down the middle. So I just draw a straight line down the middle of the problem, and you pull the GCF out of each side of that line. So in the first half of the line, we have 3x squared minus 15x. Those have a 3x in common. So when I pull out the 3x, I have x minus 5 left. When I look at negative x plus 5, whenever the first term is negative, we're going to pull that negative sign out as the GCF. And in this case, all they have in common is that negative 1. So we're going to pull out a negative 1, and that'll leave behind, again, x minus 5, which is how we know that we're doing this right, is when you get the same binomial GCF there, that x minus 5 in both spots. So we can pull that to the front, x minus 5, and that leaves behind 3x minus 1. So we now have x minus 5 times 3x minus 1, and if we go ahead and split this into two problems using the zero product property, we have that x minus 5 equals 0 or 3x minus 1 equals 0. So solving them individually, either x is 5 or 3x minus 1 is 0 would give us that x equals 1/3, because you add the 1 and divide by 3. All right, so now we got to think, are these answers both plausible? Well, we didn't do anything in this work that would give us erroneous solutions, so we should be all good, but we can always go ahead and plug them into the original problem and double check if we need to. So if I take 5 and I plug it in over here, 5 squared is 25 times 3 is 75. Okay, so we want to make sure the right side also equals 75. 16 times 5 is 80, and minus 5 is in fact 75. So x equals 5 is all good. 1/3 squared, okay, over here 1/3 squared is 1/9 times 3 gives us 1/3 again. So this side is equal to 1/3. And on the right side, 16 times 1/3 would just be 16 over 3. And we want to subtract 5 from it. So 5, if we find a common denominator, is 15 over 3. So we have 16 over 3 minus 15 over 3. That gives us 1 over 3, which is exactly what the left side was. So both of these answers are going to work. And so we can say that the number is 5 or 1/3. Okay, we have nothing that says one of those answers is better than the other. Both are equally as possible. All right, number 7. This one's going to get a little tough now. It says Abby rode 10 kilometers upstream and 10 kilometers back downstream in a total of 3 hours. The speed of the current was 5 kilometers per hour. What was Abby's rowing speed? So we are trying to find out what is her speed in still water without the current affecting her. This one we're going to use a table for. And the same table is going to apply to number 8, where this is a very common type of problem where we have to know a real life formula that relates to what's happening here. So just like in previous examples, we needed to know that area meant length times width and perimeter meant to add up all the sides. Here, we need to know that rate times time is equal to work. Okay, where this can mean a lot of things. Okay, rate can be thought of as speed, okay, how fast you're going. Time really is just time. That one doesn't change much, but it could be hours, seconds, minutes, any unit of time. And then work is what you're accomplishing, which in this case is going to be the distance that you travel. So you might think of this equation as speed times time equals distance, but the more general form is what I've written here. Rate times time equals work. And this can also be solved for whatever you might need to solve for. So for example, if we want to solve for time, we could just divide both sides by rate. We could say that time is equal to work divided by rate. Or we could have also solved for rate. We could say that rate is work divided by time. Okay, so you can solve for all three parts of this puzzle. So what we're going to do is set up a little table where we have these three variables, rate, time, and work, and we're going to try to make sense of the problem we have. So we're going to set it up as rate, work in the middle, and time on the right. And then we're just going to plug in what we know. So we know that we went on 2 trips. We went upstream and we went downstream. So if we are going upstream, I'll label this first row as up and the second run as down. If you are going upstream, that means you're going against the current. And so your speed is usually going to be quite slow because you're having to work extra hard to keep up and go with the current, go against the current. So if we are accomplishing the same thing in both directions, we're going 10 kilometers in both cases, we can go ahead and put that in for work. So going upstream and downstream, we go 10 kilometers both times. The work stays the same. The time and the rate are completely different though. When we go upstream, we are going slower than normal. So we're not going X miles per hour or X kilometers per hour, which is what we want to solve for, is that rowing speed. We're actually going to be going X minus 5. Okay, we're going to be going slower than what we're pedaling at or what we're rowing at because that current is working against us. So this current right here being 5 kilometers per hour is what's going to be subtracted from our rowing speed. But when we go downstream, so when we go the opposite direction, we're going to have a boost from the current. So it's going to be x plus 5 is our rate or our speed. Okay, so if we row at x kilometers per hour, that doesn't change. But the current is going with or against us, we add or subtract that from our speed. So going against the current, we subtract it because it's getting harder, we're going slower. But going downstream, we're going with it. So we add that speed because it's helping us. It's giving us a boost. All right, so now we don't have anything in here about time other than the fact that together it's 3 hours. So that means that the 2 times together are going to sum to 3. Okay, if we add together the 2 times that each trip took, it has to equal 3 hours. Well, how long did each trip take? So this is why I wrote this equation up here, that time is equal to work divided by rate, because that is going to allow us to write an expression for time in both cases. In the top one, work is 10 and rate is x minus 5. So 10 over x minus 5 is the time that it would have taken. In the second one, very similar, 10 over x plus 5. So now the way we're going to get an equation out of this is the fact that these 2 times have to sum to be 3 tells us if we add those together, it is equal to 3. So we're going to go ahead and take those 2 equations and say that 10 over x minus 5 plus 10 over x plus 5 needs to be equal to 3. And now we can go ahead and solve because now we have the equation that we needed. All right, solving this one is the most complicated one we've done so far because we have rational expressions, which means we are going to have to find a way to get rid of those denominators. The easiest way to do this is to multiply everything by the GCF, or sorry, the GCD, LCD, can't talk right now, the LCD, the lowest common denominator of these. So if we want to find the lowest common denominator, what we do is multiply the original 2 denominators. So in this case, the original 2 denominators are x plus 5 and x minus 5. So what I'm going to do is actually multiply everything by x plus 5 times x minus 5. So up here, x plus 5 times x minus 5. On the next one, same thing, x plus 5, x minus 5. And on the other side of the equation, same thing again, x plus 5, x minus 5. What ends up happening there is that the denominators cancel out. So in the first fraction, x minus 5 and x minus 5 cancel. On the second one, the x plus 5s cancel. And now I can just multiply out what's left. So we have 10 times x plus 5 is 10x plus 50. We have 10 times x minus 5 is 10x minus 50. We have 3, and then multiplied by x plus 5x minus 5. When you multiply the two parentheses together, that is a difference of squares. So it's going to be x squared minus 25. And if you multiply the 3 on there, you're going to get 3x squared minus 75. All right, now we have what is actually a pretty simple quadratic, although it might not look like it at this second. We're going to have a couple things cancel out here. So we have a plus 50 and a minus 50. Those cancel. And then we have 10x and 10x are going to add together to be 20x. But I'm going to move that 20x to the other side. So we're going to get 0 equals 3x squared minus 20x minus 75, where I just went ahead and stole that 20x from the left and moved it over to the right. So now this one is not going to factor nicely. Okay, and the reason I know that is if we try, it's not going to work. And so what you're supposed to do if you don't know if something is going to factor is check what the discriminant is. But since I already know it's not going to factor, we're going to check the discriminant in the middle of writing the whole quadratic formula. So we're going to go ahead and say here that x is equal to negative b, so negative b is negative 20, which is positive 20, plus or minus the square root. B squared is 400 minus 4ac. So a is 3 and c is negative 75. So we're going to have minus 4 times 3 times negative 75. And then all of this divided by 2a, which is 6. So when we work out that discriminant, which is the part under the radical here, when you multiply negative 4 times 3 times negative 75, you're going to get a positive value. Okay, we're going to get a positive value, and when we add that value to 400, it is not a perfect square. All right, the fact that this is not a perfect square inside means that we are not going to be able to factor this using the AC method or any of our other normal methods. So instead, we have to actually type in this whole quadratic formula and get a solution that way. So what we're going to do is pull out our calculator, where you can either use Desmos to have a built-in quadratic formula like I have here, or you can type it out individually. So I really just pulled this one up to show you that this is an option where you can then change what A, B, and C are to meet the criteria, or you can type it all in by hand. And so we're going to do it that way just for sake of all of us having the same screen on the same thing on the screen. So we're going to do 20, and you can't do plus and minus at the same time. So we're going to do the plus version first. It's the square root of 400 minus 4 times 3 times negative 75, and all of that divided by 2a, which was 6. If I type all that in, I get 9.34. Okay, so we can go ahead and say that one of these solutions, I need to change back to the pen. One of these solutions is approximately 9.34. And if I want the minus version, so from the plus minus, I can just go up next to this 20 and put subtraction there instead. Notice it gives me negative 2 point, and I'm going to round that to be 2.68. All right, so now we need to say what this actually means. We got 9.34 or negative 2.68. We were trying to find Abby's rowing speed. So Abby's rowing speed cannot be negative. There's no way that Abby is rowing at a negative rate because that's not even possible. Okay, so what we're going to do is throw away the impossible answer, and we're going to be left with just the 9.34. And so that is going to be our solution. So we can say that Abby's speed was 9.34, and this is in kilometers per hour. So Abby's speed in still water is going to be approximately 9.34 kilometers per hour. which means when she was rowing upstream, it was really 4.34 because you subtract the 5. And when she was rowing downstream, it was really 14.34 because you add the 5. All right, one more. Number 8 says, working together, Matham and Sapna can grade their students' projects in 2 hours. Working alone, it would take Matham 2 hours longer to grade the projects than it would take Sapna. How long would it take Sapna to grade the projects if she was working alone? So what we are trying to actually find here is how long it would take Sapna working alone. Okay, so her speed or her time, I'm going to put T for time here, is going to be how long it takes when she is working alone. So what we're going to do is set up a similar problem to what we had before, a similar table, where we're going to have rate, work, and time. Because notice that we have in this problem how long it's taking them, and we have how much work they're doing because they're grading the students' projects, so they're just doing one job. The work they're doing is one job. They're grading all the students' projects, so one thing. Okay, like that is the mission. There's only one mission, and it is grade all projects. So one is the amount of work they're doing. But we want to be able to write down what their rates are and their times. So we're going to have rate, work, and time, just like before. And this time, we're going to actually have 3 rows where we're going to have one for Matham, one for Sapna, and one for together. Okay, so we're going to have Matham's row, Sapna's row, and we're going to have a together row. So now we're just going to fill in what we know. The thing we are trying to solve for is how long it takes Sapna by herself. So I'm going to put the T in the Sapna time box. Okay, what else do we know? We know that the work they're doing is grading the students' projects. So we know that in all 3 of these cases, we're figuring out how long it takes them to do that one job. And that one job is to grade the projects. Okay, so grading projects is 1. Then we have that together, right here, together, it takes them 2 hours. So in the together column, or the together time box down here, I can put a 2. Working alone, it says it would take Matham 2 hours longer. Okay, so Matham's time here, when he works alone, is 2 hours longer than Sapna. So if Sapna's time working alone is T, then Matham's time working alone is going to be T plus 2, because it's an extra 2 hours. So now, we don't have anything in here about rates. So what we're going to have to do is use the formula, like we did before, for time to calculate the rate. So this one up here, rate times time equals work. If we divide time on both sides, we get that rate equals work over time. Okay, so down here in our rate boxes, we can go ahead and say that Matham's rate is the work, which is 1, divided by T plus 2, which is his time. Okay, so again, I get this right here by doing work divided by time. 1 divided by T plus 2. Similarly, Sapna's rate is just 1 over T, because Sapna's time is just T, and the work is still 1. And the more complicated one is the together rate. Well, the way it works when you're working together, assuming you're not getting in each other's way, is that you actually add together your 2 rates. Okay, so if one of their rates is 1 over T plus 2, and the other one is 1 over T, then their together rate is the sum of those. 1 over T plus 2 plus 1 over T. All right, so now we have the table completely filled in. We just have to use this now to write an equation that we can go ahead and solve. So when we look at what our options are, we could either turn this first row into an equation, but notice there's t's in multiple places. And so it's going to be, there's not really a way that we can solve for the t there, because we're going to have t's in 2 spots. Same with the Sapna row. But in this third one, we have t's in the rate, and then we have solid numbers, 1 and 2 for the work and time. So we can go ahead and turn this into an equation in the same way that we turned right up here time, or rate times time equals work, into an equation. So what we're going to do is use the fact that we were using before, which is that rate equals work over time to write an equation right now. So we're going to go ahead and say that rate, which is 1 over t plus 2 plus 1 over t. Okay, remember that this is the together rate right here. Okay, same thing. This is going to be equal to work over time, which is 1 over 2 in this case, where all I'm doing is dividing this work by this time here. Okay, now we can just go ahead and solve. This is a rational equation, which is going to end up looking like a quadratic in just a second. So just like in the previous problem, we're going to want to multiply everything by the lowest common denominator. So if I give myself a little space here, I can write that LCD in. We have t plus 2, t, and 2 as denominators. So I'm going to multiply everything by 2, t plus 2, and t. Okay, so it's all three denominators multiplied together. 2t plus 2 and t, 2t plus 2 and t. When I do that, we're going to have some things cancel from each fraction. So t plus 2 and t plus 2 cancel in the first one, t and t cancel in the second one, and 2 and 2 cancel in the third one. So then we multiply out what's left. In the first fraction, we just have 1 times 2 times t, so that's 2t. In the second fraction, we have 1 times 2 times t plus 2. So if we distribute the 2 and the t plus 2, we get 2t plus 4. And from the right side, we have t plus 2 times t, which is going to be t squared plus 2t. And hopefully now you can see it's a quadratic. Because we did that t times t on that right side, we end up with the t squared. So now getting everything on the right side, we're going to have 0 equals t squared. And if I add together the two t's right here, these ones, this is 4t. And if I subtract 4t over, 2t minus 4t is going to be negative 2t. And then we subtract the 4 over also to get a minus 4 there. Okay, this one is not going to be factorable just like before, because again, if we try the discriminant, we're going to get a non-perfect square. So what we're going to do is set up the quadratic formula again. We're going to say that t is equal to negative b plus or minus the square root, b squared minus 4ac. In this case, 4ac is nice and easy. It's 4 times 1 times negative 4, which is negative 16. So we're going to add here to get positive 16 because there was already a negative. And 2a is 2. If we simplify this just a little bit, 4 plus 16 is 20. And so the square root of 20 is going to simplify. So we have 2 plus or minus the square root of 20 all over 2. The square root of 20 is actually just 2 root 5. So we have 2 plus or minus 2 root 5 over 2. And then if we divide everything by 2, we get 1 plus or minus the square root of 5. That is the exact version of the answers, or at least the possible answers. But just like in the previous problem, we're going to get a decimal approximation because if you told someone it's going to take you 1 plus the square root of 5 hours, they're going to look at you like you're crazy. So you want to be able to give them a more tangible answer, something that they can understand. So we're going to go ahead and come over to our calculator, clear that out, and say 1 plus square root 5 and 1 minus square root 5. We get two approximate answers here. T is approximately either 3.24 or negative 1.24. And in this case, we are talking again about time or a rate. We're talking about how long it's going to take Sapna to do this thing alone. So there is no way that's going to take her negative time to do this job. And so we can say then that 3.24 must be the correct amount of time. So it would take Sapna 3.24 hours. And in this case, we mean that it would take her 3.2 hours to complete the job of grading all the students' projects if she was working alone. So working with Matham, it only takes 2 hours. Working without Matham, it takes 3.24, which means, Matham is not quite as productive. And real quick, if we wanted to know, we could also say how long it takes Matham, because his time is an extra 2 hours. So if Matham did this job alone, it would be 5.24 hours to completion. All right, hopefully you're seeing that math is all around us, especially quadratics and linear equations. And hopefully you got a little bit of confidence about how to set some of these up. I know some were quite challenging, but hey, it's mathematics. It's meant to be a little bit hard. So see you guys on the next one.